All right. Hello, everyone. I just started the recording, so I'm going to move to the PowerPoint. So essentially, this is tutorial 10. I know that it says tutorial 9, but this is the second problem that I had originally planned to work on 11/19. So, but I'm traveling, so I'm recording this tutorial as tutorial 10, and I'm just going to add it to these slides. But this will be in place of me having an in-person session on the 26th. So there will not be an in-person session on the 26th. And I'm going to talk with Dr. Vassal about sending out a reminder update message, I guess, about that. So this is probably not even necessary for me to tell you here, but anyways. So last time I did one problem, and it was an application of the Navier-Stokes equations to look at the derivation for Bernoulli's equation, taking a look at irrotational flow, and satisfaction of the continuity equation as well. So I went into some detail about, sort of like where the simplified versions of these equations come from. I didn't want to just like start with the simplified version, and you'd be wondering like where that come from. Maybe you wouldn't be wondering, but I would have been wondering before I had a class like this and had advanced fluids. So, um, so I figured I'd go through that exercise of listing out all of the Navier-Stokes equations, which is this bit on the kind of the bottom of the screen, bottom half, and then applying all these red assumptions to zero out a bunch of these terms, and eventually get to the simplified version in this top left section. And yes, so I guess I can use the laser pointer. Here we go. Yeah, so this section here are the simplified versions, and then we ended up, kind of running with that and solving the rest of the problem. So what I will say is there are some questions on here. I'm going to meet with Dr. Vassal, ask these questions. That way you'll have some, maybe a clear idea of some of these things. I just want to confer with him before I tell you one way or the other with too much definiteness. So with that, I'm going to move on to, oh, here we go. Okay, I'm going to move on to problem number 2. So this problem is, it's similar to the previous one. It's an application of Navier-Stokes. What's on the screen right now, one is a question I'm going to ask Dr. Vassal, and the other is is an explanation I'll come to here in just a moment. So we'll start with saying, we'll list our givens. So the problem says a viscous liquid of constant density and viscosity falls due to gravity between two parallel plates a distance 2h apart, as in the figure. So we have this distance here, 2h. The flow is fully developed. That means that W is only a function of x. This bit right here, W is only, that's important, a function of x. So that is the picture on the right-hand side. What that's saying is as you fall down this channel, let's say like we have 0.1 here, 0.2, time. These are like, let's say just kind of like time t equals 0 and some time later. You could say like, I don't know, 10 seconds later or something, 10 minutes later, sometime later is this kind of 0.2. Fully developed is saying that the velocity profile, this is the velocity profile we are looking at. It is only going to change as we traverse in the x direction. So like this curve, if you move left to right, it's changing the velocity of the fluid. But if we advance down the pipe, the profile is the same. So it's like advancing down the pipe, profile doesn't change, but the profile does change moving left to right. If that's x and this is y. So a little bit, I remember struggling with that concept in advanced fluids of like, it looks like it's changing with y too, to me, it did to me at the time. But basically, it's just saying like, as you move left and right, the velocity changes. But as you move down the pipe, down the flow, you have a consistent velocity profile shape. And I guess magnitude as well. It's not changing. Whereas on the right-hand side, so this is fully developed. I'm going to denote that clearly. And this is not fully developed. Because you can see that velocity profile is like changing as you move down the pipe. Okay. So that's all I want to say there. There are no pressure gradients, only gravity. That's a good simplification. So we want to set up and solve the Navier-Stokes equation for the velocity profile W of x with respect to x. W is a function of x, you might say. So, okay, so givens, I guess, we have the figure. We know that W is only a function of x. We've already reviewed that. We'll say no dp dx, no dp dx, no pressure gradient. And then I'll put only gravity, G. Only gravity. And so our find is set up and solve the Navier-Stokes equation for the velocity profile, which is W of x. Okay. So what I'm going to do is I'm going to fully write out the 3 dimensions of Navier-Stokes, x, y, and z, if you're using Cartesian coordinates. And I'm going to do that just because I think it was really helpful for me to get to see these written out a few times and to see the simplifications, applied. So since I got a little bit of time to do this, then I'm just going to write it out because I feel like it would have helped me as I was sort of visualizing these problems. So Navier-Stokes, like I said, I'm going to write these x, y, z for Cartesian coordinates. But as you'll probably see later, you could solve these in not rotational, cylindrical or spherical coordinates. Those are both valid options as well. But we're going to do Cartesian. So Cartesian. I think I spelled that right. Yeah. Yeah, I'm going to assume I got that right. So, all right. So let's go and list out the three components of Navier-Stokes. So for x, we have rho, then we have du dt, where u is the x velocity. Then we have du dx u plus du dy v plus du dz w. You can notice here that we're evaluating how the x velocity is changing in each of the directions, right? So then we have negative dp dx. That's pressure gradient, right? And then we have plus mu, our viscosity, times d. Let's see. You can do it, bud. Let's see if I can get this to cooperate. Here we go. Du squared dx squared plus d squared u d y squared plus d squared u dz squared. Okay, and then we have this plus the gravitational term, rho gx. Okay, so that's the x component. Like I said, y and z are very similar. Rho, basically the only change is we have y, gravity, pressure gradients with respect to y, and then instead of those u's in the numerators, we get v's. Because now we're looking at the y velocity v. So, and this is stuff you all probably know, but it's just good reiteration. Okay, there's dB dx u plus dv d y v plus dv d zw. Okay, equals to negative dp dy plus mu d squared v dx squared plus d squared v dy squared plus d squared v dz squared. Okay. Plus rho gy. Okay, and then z component. Same thing, now we use w instead of v. Based on kind of like the explanation I had before, gave before. So I'll just write this butt out. dw dzw. Okay. Okay, so that is, those are the three different components of the Navier-Stokes equation, x, y, and z. Now, we can go and apply assumptions. So I did make a slight error here. I called this dp dx. This is actually dp yeah, I guess I made two errors here. So this is dp dz. We have flow in the z direction. If you pay attention to the diagram, that is the z direction. So the first mistake is that we don't have a pressure gradient in the z direction. We have flow in the z direction. So it's saying, when it says no pressure gradient, it's saying there's no pressure gradient in the z direction, since that's the way we have flow. Now, the second mistake was here on these on my little diagrams over here. I put that as y, but I'm going to make it z to be consistent with the problem statement. Okay. Okay, so the next thing we want to do, like I said, is we want to apply assumptions here. Now, well, something has happened. Okay, we're back, I think. Cool. So, these assumptions are actually like pretty, I guess you might say, why'd you even write it down to begin with? Because we have z flow. But basically, you can mark out that guy and that guy. Why? Because there's no flow in x direction. And there's no flow in the y direction. So you just mark those out, right? If you look at our profile here, we have flow along the z-axis. Now the flow velocity profile changes with x, but the flow itself is moving this way, right? Even if those vectors change in like, their like magnitude as as you kind of follow this velocity profile, even if that's the case, the flow is still only in the z direction. So the magnitude of the vectors changes with x side to side, but the direction of it is still only in the z direction. That's the important point there. So you can cross out y Navier-Stokes and X Navier-Stokes because all of those U terms, du dt, du dx, du dy, are all going to be 0. The pressure gradient in the x direction is 0. So I guess that's another interpretation of no pressure gradients. No pressure gradients. So I guess that is saying that dp dx equals dp dy, which equals dp dz equals 0. Okay, so that's a fair point, I suppose, to make there. Okay. But then, and then these, d squared, or yeah, d squared u, dx squared, so on and so forth. All those are going to be 0. And we're going to take gravity based on the picture there as in the negative z or in the positive z direction, I guess. So long story short, you zero out the x and y Navier-Stokes equations. Now, looking at the z direction, what do we need to see here, right? So if it's fully developed, then well, I guess that's not, let me say this. So this u is 0 because there's no flow in x. This v is 0 because there's no flow in y, right? So both of those can go away. Let me make sure it looks like a z there. Okay. Then what else do we know here? We know that the w, or z velocity, only changes with x, right? That was the previous statement that we made right here. So that means that the derivative of w with respect to z is 0 because it only changes with respect to x. Okay. W only changes with respect to x. So that zeroes out those three terms. And then what we can say is on the right-hand side, we know there's no pressure gradient, right? So that is 0. That was a given. Now dw dx, or d squared w dx squared, that is going to stay because we know the w changes with x. So that's good. But these are both going to be 0 because w changes with respect to x only. So I'm going to mark both of those as 0 for the same reason. And then gravity stays because we have gravity. That's stated in the problem. Okay. So next. Then one more assumption that we need to make. This is one more. Because this is fully developed flow means that sufficiently enough time has passed for the flow to not be changing anymore. It's fully developed. It's gone through the developing process and it's now steady state. So with that in mind, set dw dt equal to 0 because it's not changing with respect to time anymore. It's steady state, it's fully developed. Okay, so fully developed steady state. All right, lots of assumptions, lots of simplifications, I might say. So that will leave us with a much nicer looking equation of, and this is just the z portion, like I said, so we're going to go down to one equation here. 0 equals to mu d squared w d x squared plus rho gx. Right, so that's good. That's good. Now, oh, I'm sorry, gz. Gz. Okay. And here I'm going to rewrite this to make it match the picture, because the picture is called gravity g. But it was aligned in the positive z direction. So got this guy. This is rho. I'm just gonna plug in g here. Okay. And again, that's it. The g is aligned in the positive z direction. That won't be the case in all of your problems. Will not be the case in all your problems. Okay, so now what we want to do is we would like to know what it asks us for. Set up and solve the Navier-Stokes equation for w of x. So let's find w of x. How do we do that? We integrate, right? So we want to rearrange this as get w d squared w dx squared on one side, and on the other side, get everything else. Okay? So let's go ahead and let's integrate both sides. That's going to give us that's going to give us d w dx equals to negative rho g over mu x plus c1. Okay. And then integrate again. We get w of x is equal to negative rho g over 2 mu x squared plus c1x plus c2, where that the 2 came from that integration of x to x squared over 2. Okay, so with that in mind, what else should we do here? So thinking through what's the next step here. All right, so I guess now what we want to do is we need to apply some boundary conditions to solve for our constants of integration there, right? Because these constants here, it's like, I don't know, what are those? We don't know what those are. And then that's the last part of this problem. So, okay, solve for constants of integration. How? By applying boundary conditions. Okay. Boundary conditions, BC. As well, I'll abbreviate that too. Okay. Number one, first boundary condition is the velocity at negative h, which, if you look at this picture, right, negative h is at the wall and positive h is at the wall, since the origin is kind of in the middle of the two plates. So that's where the x direction starts. So we have w of negative h and w of positive h. The velocity, both of those locations, is 0. Why? Because of no slip condition. Okay. So I'm going to switch pages and apply those. So what we get is, if we apply that first one, what have I done? Okay. I think it's working now. Okay, so for the first condition, plug that into our equation, and we're going to get 0 equals negative rho g over 2 mu negative h squared plus c1 times negative h plus c2, right? And then we apply the second condition. We're going to get 0 is equal to negative rho g over 2 mu positive h squared plus c1 positive h plus c2, right? So what can we do there? What we can do is we can say that we can solve one of these for C2, right? So we could say solve, let's just say this first one for C2. So C2 is going to be equal to rho rho g over 2 mu h squared plus C1 if we move that over to the other side. Now plug into that guy, and we'll get 0 equals to negative rho g over 2 mu h squared plus C1 h plus rho g over 2 mu h squared plus C1. Okay. Oh, there's an h here. Yes. Okay. So now, as you can probably tell, those guys cancel, and we're left with 0 is equal to 2 C1H, or in other words, C1 equals 0. Very nice. Very convenient that that is the case. So now plug it back in and see what happens, right? So I'm going to plug it into the second equation again. w of positive h equals 0 equation, just because I like those positives better. So we have a negative rho g over 2 mu h squared plus c1h, I'm sorry, c0 times h, because c1 is 0, plus c2. So now we give that a solve, and we'll get that c2 is equal to rho g over 2 mu h squared, right? So then plug that back into now our original equation, go back to the x's version, the version with x's. So go over here, w of x is equal to negative rho g over 2 mu x squared plus c2, but c2 is rho g over 2 mu h squared, right? So now let's just rearrange this a little bit, make it look a little bit cleaner. And so last thing, very last bit here is we could say rho g. So I'm taking this out, this common term, I'm taking out of these two terms. Common factor, I should say. There we go. That is the final answer right there. So that is the velocity profile in the z direction that varies solely with respect to x. And that is the result of us wanting to set up and solve the Navier-Stokes equation for w of x. That's the answer there. So, yeah, hope that was helpful. When I took advanced fluids, it was basically a whole course of just this. It was just like, here's a scenario, need you to apply assumptions, do some integration, apply boundary conditions, but like for a lot of different scenarios. And then there was other stuff too, but that was a big portion of it, was just studying different types of flow and getting comfortable and familiar with the Navier-Stokes equations. So I hope that going through that kind of step by step is clarifying. I know that that was for me when I was looking at this for the first time. So if you have any questions, just let me know about this recitation or the previous one. Like I said, I'm going to upload, this is number recitation 10, but I'm going to upload it with the slides for 9 since they kind of go together, and that was the original plan. And yeah, hope you all have a nice Thanksgiving, and I will see y'all after the holiday.